Okay, let's start for today. In our last lecture, we started discussing how we can compare quantum states, right? And the first quantitative measure that we introduced with which we can compare two quantum states was the trace distance. And we've seen that the trace distance is particularly useful because it is actually a metric on the state space of density operators. So we can really use it to measure distances between quantum states. We've also seen that the trace distance has interesting and nice properties, such as it being invariant under unitary transformations, or that it provides an upper bound for the classical trace distance. Right? If we perform any measurement, then this is an upper bound for the classical trace distance that we get out from the measurement. And we've also seen that it's constructive on the trace-preserving operations, and it is strongly convex. Right? So these were the properties that we stated. And we then continued with another quantity with which we can compare now two quantum states, which was the quantum fidelity. And I think we then ended up, so at the end of last lecture, we stated Uhlmann's theorem, which we're now going to prove. So let me now start with stating again Uhlmann's theorem. So this was theorem 3.7. That's Uhlmann's theorem. And Uhlmann's theorem says that two quantum states, so let rho and sigma be density operators, or simply say states on the Hilbert space H. And then the fidelity of rho and sigma is given by a maximization over purifications phi and psi, and we maximize over the overlap, so over their inner product. This was 386, and where the maximization is over all purifications. It was psi, which lives in the Hilbert space H tensor H of rho, and phi in H tensor H of sigma, right? Let's now prove this theorem. The proof is going to take us some time, and in particular, for the proof, we need three intermediate results. Okay, so I first prove three intermediate results. With using these, we can then easily prove the theorem. So the first thing that we want to show is that for any operator A and unitary U, we have the following. We have that, I stated here, that modulus of the trace of U A is smaller or equal to the trace of the modulus of A. So this is 3.87. Okay, we're going to prove this now. Proof of 1. And the proof is as follows. So I forgot to tell under which conditions there is the equality. Sorry. So with equality, if U is equal to V dagger, where A equal to V modulus of A is the polar decomposition sorry, I forgot to mention this. So remember that the polar decomposition, which states that for any operator we can bring this in this form with V unitary and A being the modulus of the operator A. right? So and equality is the case. So the inequality saturates if U is V dagger. Okay, so let's prove this. The proof is as follows. So we take a look at proof of 1. So take a look at this quantity here, trace of UA, and we write A now in this polar decomposition. So write V modulus of AU. Okay, and now we split A as trace of V and then the square root of modulus A, and again the square root of modulus A U. Okay, and as a next, we use the Cauchy-Schwarz inequality for the so-called Hilbert-Schmidt norm. So using the Cauchy-Schwarz inequality for the Hilbert-Schmidt norm, you may not know it, so let me state it. It's that AB modulus squared smaller equal to AA times BB, where this AB is equal to the trace of A dagger B. So this is the so-called Hilbert-Schmidt norm, right? And it satisfies the Cauchy-Schwarz inequality. So we're not going to prove this. So this is generally known, so to say. This yields. So we apply now this, and we say, okay, this here is what we here call A dagger, and this is what we call B. So we get the modulus of trace V A dagger U is then smaller or equal to the square root. Square root of, we have the trace of A dagger A, which gives us something like V, square root of modulus A, square root of modulus A V dagger times the trace of, now we need B dagger, which is U dagger, then modulus A, square root of modulus A U, and the square root thereof. So let me number this. This is 3.87 and this. So you see that using the cyclic property of the trace, those unitaries V and U, they vanish, right? So we get then equals trace of modulus of A, trace of modulus A, and this is equal to the trace of the modulus of A, okay? So it's exactly what we want. If you now look at 387, now what remains is the condition under which the inequality saturates, right? And it states that inequality saturates if we take U as V dagger, right? Because then, so if U is equal to V dagger, then we have that the modulus of a trace U A is equal to the modulus of the trace of U is V dagger, so V dagger, and then the polar decomposition V modulus of A, right? So this is the modulus of trace of the modulus of A, and this is trace of modulus of A. Okay, this proves now our first statement. Okay, the second statement that we need is the following. So they are considered two quantum systems. Let's call them Q and R. So for our principal quantum system and the reference system. With the same Hilbert space. Call it H and ON basis. Basis, say we have IQ and IR of Q and R respectively. So these are ON basis and ON basis of our system Q and this ON basis of system R. And both are of the same, both live in the same Hilbert space. And then for operators, A on Q and B on R, we have with the maximally entangled state, let's call this M, equal to the sum over all IQ, IR. So it's not necessarily normalized, right? Because this is an ON basis, but let's define M like this. Then for these two operators, we have the following equality, namely the trace of A, B transpose, so this is a transpose, is equal to M, and then we have A tensor B, and again M, this is 388. So in here, so this is a matrix multiplication. It's the matrix multiplication of the matrix representation of operator A and B in the basis I, which we stated here, right? So with the matrix multiplication with respect to the matrix representation in the basis IQ and IR. Okay, so this is our next result that we that we prove. The proof of 2. Okay, to this end, let us first take a look at this matrix multiplication. So, using that the matrix multiplication A, B transpose, and now we have, say, the J case component of this, is given by the sum over L, and then we have A J L times B transpose LK, where this matrix elements A, J, L are as stated here in this basis I. So this is then JQ, and here with LQ, with and similar for B. So we have then B transpose LK is equal to LR, B transpose KR. So if we use this, we get for this trace here. So we can now calculate this trace. So we have trace of A, B transpose. Well, the trace is simply now summing over all diagonal elements of this. So we simply sum over all L of A, B transpose LL. Okay, these are all diagonal elements of this matrix representation. And now we can use this and plug it in. So we have then sum over L. AJL is given here with JQ, A, LQ. And then here we have B transpose LK. It's here, so we have L, R, B transpose, and then again L, sorry, not L, this is wrong. Okay, here, let's give here another index. Let's state that this is J. So J, then we have sum over J and L. So we have J, JL, JLL, J. Sorry, I just mixed up the indices. So we can now use this transposition of this operator B, or say the matrix B. Okay. Transposition is simply exchanging rows with columns and columns with rows. So if you do that, if we go back to our usual operator B, then we find that this is equal to sum over JL, and then we have JQA LQ, and then we have, so we have here JR B LR. Right? Now note that this is not transposed anymore. And this is equal to M A tensor B M. Okay? So I can provide one more line. Possibly that's easier to see. So we have sum over J, JQ, JR, and then A tensor B sum over L, LQ, LR. Okay, now you see it. So this is M, A tensor B, M. And this is what we wanted to prove. So we just proved our second intermediate result, and now the third one follows. Namely, for those quantum systems Q and R, so Q, R, and for the state M as in 2. So again, we have two quantum systems with the same Hilbert space, and this maximally entangled but not necessarily normalized state M. Then any purification say psi living on Q tensor R, so on this Hilbert space, or living on, okay, let's call this H tensor H. So for any purification psi of the quantum state rho living on H, can be written as follows, namely psi is equal to the square root of rho times uq tensor ur acting on M. So this is 389, where uq and ur are unitary. Okay, so this states that we can write any purification of psi in this form, where uq and ur can be any unitary, right? And we proved this now by first showing that this is indeed a purification, and then we argue that any purification must be in this form. Okay, so first we show that psi is a purification. Okay, therefore, we first rewrite it by plugging in M. So the proof of our intermediate result 3. So we write psi as square root of rho uq tensor ur, and now we plug in the state M, so which was the sum over j, jq, jr equal to the sum over j. Now we have square root of rho uq acting on jq tensor ur acting on jr. Okay. Now let me redefine these basis states, because this is simply a unitary transformation. So I can write this as the square root of rho, and then let me call this j tilde q and j tilde r, where j tilde q is equal to uq jq and j tilde r is equal to ur jr. So this is simply a basis transformation, right? So we can again write this as these states, and they again form also normal basis, because we simply did a unitary transformation. Well, now as the next step, we show that this is that this state psi is a purification. In order to do so, we have to trace out this reference system R. I think I didn't state that rho must live on the system Q. I think I only said that it lives on the Hilbert space H. But indeed it lives on Q, right? So this state is living on actually Q and R, and this lives on Q, to be precise, right? So let's now take the state psi and trace out the reference system. So we have that the trace of psi, the partial trace over the reference system, is given by the partial trace. Let's plug this in. So we have sum over jk, and then square root of rho j tilde q, k tilde q, square root of rho, tensor j tilde r, k tilde r. Okay. In this form, it's easy to see what happens if we trace over the reference system. So what it gives us is a delta jk. So one of these sums is compressed, and we have this form here, j tilde q, j tilde q rho, right? And now we can put the sum in here, such that we have rho sum over j, jq square root of rho, and this, you can see, this is the identity, it's the completeness equation, and we get square root of rho times square root of rho gives rho, and with this we see that psi is indeed a purification of rho, right? But this, yet it doesn't finish the proof, because the claim is that any purification can be written in this form. We just showed that this is a purification, right? And in order to see that indeed any purification can be written in this form, we have to briefly recall the Schmidt decomposition theorem. Okay? So remember the Schmidt decomposition theorem, and in particular the Schmidt decomposition theorem is unique up to local unitary transformations of our bipartite system. So, okay, let me briefly recall. Schmidt decomposition tells us that we can always write a bipartite state in the form, so for psi living on HA tensor HB, and we can always write psi in the form of sum over j, and then we have the Schmidt. I think we introduced it as square root of lambda. I think it was the square root of lambda j, and then we have some basis states lambda j of this reference system A, and then some basis states lambda j, or we called it possibly Vj of system A, and call it Wj of the system B. Okay, but there's only one sum. This was the Schmidt decomposition theorem, and this representation is unique up to unitaries, so up to unitary transformations of these local systems. Okay? And since any pure bipartite state is unique up to unitary transformations of these two systems, we see that this purification is also unique up to unitary transformations of either reference system Q or R, right? However, here we have that we also started from arbitrary unitary transformations in these systems, and this finishes then the proof that indeed any purification can be written in this form. So, by the Schmidt decomposition, which is unique up to unitary transformations of the UN basis, we find that any purification of rho can be written as in equation 389. Okay, so this proves the third statement. Okay, and now, as I told you, with these three intermediate results, we are now set to prove Uhlmann's theorem, which is our goal. So we are now set to prove Uhlmann's theorem. Okay, suppose that this psi equal to square root of rho uq tensor, or u, I think I called this u, yeah, uq tensor ur acting on the state M is a purification of rho, and the state phi equal to the square root of sigma vq tensor vr M is a purification of rho, of sigma, sorry. And clearly, uq, ur, vq, and vr are unitary, right? Then we get the inner product, because remember that Uhlmann's theorem considers on the right-hand side of the equality this inner product of the purifications, right? So we can now calculate this by considering these two purifications, because we know that any purification can be written in this form for some unitary. So let's plug this in. We have there M, and then we have u q dagger square root of rho tensor u dagger r, and then we have square root of sigma vq tensor vr M. So we can write this as M, and then we have here u q dagger square root of rho square root of sigma vq tensor ur dagger vr, and the next thing we do is you see that this is in the form of our, I think it was the second of our second intermediate result, where we had here something which was denoted by A and here by B. Right? Remember, this was trace of A, B transpose was equal to this expression of M, A tensor B, M. This was our second intermediate result, and this we're going to use now. So unfortunately, it's not on the blackboard anymore. So using, but I can write it down, using that trace of A, B transpose is equal to M, A tensor B, M, from equation, I think it was 388. We get now that the inner product of phi and psi is equal to the trace of, now we have A, which is given by U, Q, dagger, then rho sigma VQ, and then we need B transpose, which gives us VR transpose, and then UR dagger transpose. But UR dagger transpose is simply the complex conjugation of UR, right? Okay, now let's bring this in. Let us use the cyclic property of the trace and bring U to the other side. So we have trace of rho sigma and then VQ, VR transpose, UR star and UQ dagger. Okay, let's now denote this term by U. So this is unitary. We are just having some unitaries here. And as we've then now it's in the form of our first intermediate result. So next we use this. The first result was the trace of some arbitrary operator A times U is smaller or equal to the trace of modulus of A. This was from equation 3.87. We find that the modulus of the inner product of phi and psi is smaller or equal to the trace of the modulus of rho sigma. Okay, now remember what the modulus of an operator was. It was the square root of the Hermitian conjugate of the operator times the operator itself. So we have then trace of the square root of this operator dagger is simply let's rewrite this a bit. So let's simply write this. We can now switch sigma and rho. Okay, I don't know if you can see this. Otherwise, it's easy to show it, right? But it doesn't matter for the result. So let's do this just to get to the original form that we had for the fidelity. So we can do this, and now we use that the definition of the modulus of an operator, which gives us the square root, and then square root of this gives square root of rho, square root of sigma, and then we have square root of sigma, square root of rho, which is the trace of the square root of rho sigma square root of rho. And remember, this was our definition of the fidelity. Okay, I just flipped these two terms because I wanted rho to appear as the square root and sigma like this, because I think we defined it in this way. But we can also flip it because the fidelity is symmetric, and that's the reason why we can flip it here as well. But we are not finished yet, because what we showed is, we just showed that the fidelity of rho and sigma is greater or equal to psi phi. And now we have to find, so we only proved this inequality, but Uhlmann's theorem states that the equality holds for a maximization over the right-hand side. Okay, and now let's see whether we can find this, whether we can find such purification, such that we have equality. And for this, remember what freedom we have. Okay? The freedom we have is choosing those unitaries. Those 4 unitaries that we combined here into U. So we had the unitary VQ, VR, UR, and UQ. And we can now choose those unitaries and hope that we get the equality. Okay? But of course, we have to choose wisely. So for this, consider the following to see that the inequality can be saturated consider the polar decomposition of square root of sigma square root of rho. Let me write this as V, a unitary V times the modulus of sigma rho. Okay, so let this be the polar decomposition. And now you see how we have to choose U, right? Because up to here we have an equality and the inequality comes in here. So if U is equal to V dagger, then we get an equality. Do you see it? So if we take this equation and plug in here the polar decomposition, right? Then we have V times the modulus of this square root rho square root sigma times U, right? Which has this form, but we have here a V and a U. And if we choose this U to be V dagger, then we can use the cyclic property of the trace. And since it's unitary, it cancels, and we have the equality. Okay. Can be said, consider to see that the inequality can be saturated. Consider this. Okay, let's plug this in. So we have then psi phi is equal to the modulus of the trace, and then we have V times rho sigma times U. Now by choosing okay, let's choose VQ be identical to VR being equal to UR being the identity, and let's choose that UQ dagger is equal to V dagger. Then we have that psi phi is equal to the trace of modulus of rho sigma. Okay, now it's almost no space, but I think this you see. So we are here with the equality, and the meaning that the inequality saturates. And the inequality saturates. So this finished the proof of Uhlmann's theorem. And I also briefly mentioned last time why Uhlmann's theorem is so important, because from the theorem itself we can directly infer useful properties. And we're going to continue with this after the break. Okay, let's continue. Before the break, we just proved Uhlmann's theorem. And I'm not writing the full theorem down, but what we simply proved is that the fidelity, so Uhlmann's theorem says that this can be written as a maximization of the purification phi and psi, and we maximize over the overlap, so over the inner product. And from this form, as we already mentioned, I think in the last lecture, we can read off properties of the fidelity. Okay, so let me formulate this. It's remarks. So from Uhlmann's theorem, the following properties of the fidelity directly follow. So it's first, the fidelity is normalized, meaning that that it lies between 0 and 1. Second, that fidelity is equal to 0 if and only if rho and sigma have orthogonal support. And then number 3 is that f of rho and sigma is equal to 1 if and only if rho is equal to sigma. And then number 4, it's symmetric. And number 5, it's invariant on the unitary transformations. So we have f of u rho u dagger u sigma u dagger is equal to f of rho sigma. Okay, so I think we already discussed all of these properties, but I just wanted to summarize them such that you can directly see from this. I mean, there's no proof needed, I think, because you directly see this from Uhlmann's theorem. Okay, now let us now briefly recall what we also learned about the trace distance. So for the trace distance, we stated one interesting theorem which connects the trace distance to the classical trace distance, right? And there we've seen that the trace distance is an upper bound of the classical distances that I get out if I perform a measurement on this system rho and sigma, and then calculate the classical trace distance. So this provides now a connection between classical trace distance and quantum trace distance, and a similar property holds for the fidelity, right? And now, since you remember that fidelity is a similarity measure, unlike the trace distance. The trace distance was a distance measure, and fidelity is a similarity measure, meaning that kind of the invert property holds for the fidelity. And this is now also the fact by the connection to this classical fidelity, namely the quantum fidelity is now a lower bound of the, so the quantum fidelity is a lower bound of the classical fidelities if we perform measurements on rho and sigma. Okay? And this is our next theorem. So it's theorem 3.8. So let the set EM be a POVM. And let the probabilities PM equal to trace rho EM and the probabilities QM equals to trace sigma EM be the output probabilities. By measuring rho and sigma. And then the fidelity of rho and sigma is given by the minimization over all POVMs of the classical fidelities F, PM, QM. So equation 399, where the minimization is over all POVMs. So in the case of the trace distance, we had a maximization. That's the only difference. And again, this now connects us, connects the classical with the quantum fidelity. So it's a very useful theorem because it kind of connects a quantifier which takes as an argument elements from the state space. So this is something abstract, right? And on the right-hand side, we have measurement results. So this is what you measure in the experiment, right? And this is a quantity of our density operators, which is a rather abstract thing. Nothing that you directly measure in the experiment, but you can extract it from measurements in the experiment. So let's prove this theorem. And for the proof, let us first note the following. First note that by the polar decomposition, we have that sigma square root of sigma square root of rho can be written as u dagger and then the modulus of square root sigma square root rho, okay, where u is unitary. So this was the polar decomposition. I now wrote this unitary as u dagger, so I can specify this unitary however I like, right? And for simplicity, I now state this as u dagger. And we've seen that this here, so on the right-hand side, is nothing else but the square root of rho sigma square root of rho. Hence, we have that u times square root of sigma square root of rho is equal to this expression here. Okay, with u some unitary. This is why I choose this to be u dagger, because we're going to use this expression now. And then we can write the fidelity as follows. And then we have the fidelity of rho and sigma, which was the trace of this expression here, right? So this was how we defined it. So instead we can now write it as the trace of u square root of sigma square root of rho. And what we're going to do is now we insert the identity here. So we have u square root of sigma, and then we insert the identity, and then we sum over m and those measurement operators em. So this was the completeness relation of our operation, of our measurement operators, right? So we can put out the sum. And then we have trace of u square root of sigma, and then let me write this as square root of this measurement operator em, square root of measurement operator em, and then square root of rho. So this is equation 3.100. And now we use again the Cauchy-Schwarz inequality from the Cauchy-Schwarz inequality for the Hilbert-Schmidt norm. This is we just saw this Cauchy-Schwarz inequality before the break. So next we use the Cauchy-Schwarz inequality. Which was the trace of A dagger B smaller, namely the modulus square thereof smaller equal to trace of A dagger A times trace of B dagger B. Okay, we can here identify now this as A and this as B. So we then have that the fidelity of rho and sigma is smaller or equal to the sum over m, and then we have the square root of trace this is A dagger A, so we have this is A dagger, so then this is EM rho U dagger U sigma EM times the trace of the B dagger B, so then this gives square root of this EM square root of rho. So now we can use the cyclic property of the trace, and this is the identity. Sorry, this must be A dagger B, then it's wrong here. So then we have U sigma EM sigma U dagger. So we use the cyclic property, then we have U dagger, which is the identity, meaning this gives us trace of sigma EM, and this here gives trace of rho EM. Okay, meaning this is trace of, this was the definition of this factor QM, and this is PM, which is our classical fidelity. Okay, so we just proved that the fidelity is a lower bound of this, right? And what remains to be shown is that the inequality saturates for some P of m. Okay. And for this, use the time when I erased the blackboard to think about under which conditions this inequality can saturate, right? So we use the Cauchy-Schwarz inequality and think about when does it saturate. So it's up here in the upper right corner. So ask yourself, under which condition does this inequality saturate? So it clearly saturates if if A dagger is equal to B dagger, right? Then it's trivial. And what if some constant times A dagger is equal to B dagger? Does it then saturate? So the answer is yes. So if you have some constant times A dagger is equal to B dagger, then this inequality saturates. And indeed, this is the only case when the Cauchy-Schwarz inequality saturates. So we can use this now. So the Cauchy-Schwarz inequality okay, now I'm not sure whether it was correct what I just said. It does saturate if some constant times A dagger is equal to B dagger, but I'm now not sure anymore whether this is an if and only if. So it depends possibly on the operators itself, right? But in general, this might be true, but I'm not 100% sure, but possibly it's right. But we only need an if condition. So the Cauchy-Schwarz inequality saturates if some constant, if Cm A dagger is equal to B dagger for any constant now, since we have different m's, so we have for any set of coefficients Cm being complex, that is, we require that Cm and our A was here, Cm times U sigma, and then square root of Em is equal to square root of Em square root of rho, right, for some set of constants Cm. Now, let's rewrite this a bit. So now assume this is 3.102, and this was, I guess, 3.101. So now assume that rho is invertible. It means that it's positive definite. Remember that density operators are positive semi-definite, not necessarily positive definite. Okay, but for the moment, assume that it is positive definite, meaning that we can invert it. Okay. Then let's add this here. Then we have Cm U square root of sigma square root of rho, and then we take rho to the power of minus 1/2 Em so, and this expression here, we know this expression here. Okay. Where is it? Here. Here, U times square root of sigma square root of rho. It's just this expression. Take big square root of rho sigma square root of rho, and then we have rho minus 1/2 Em equals Em rho. So this is, and now let's multiply. There's a mistake. I didn't use B dagger. This is B. Then B dagger is different here. Sorry, this must be different. It must be square root of rho square root of Em, because I'm inserting B dagger in this B, so I have to flip this. So then this is here, square root of rho square root of Em, square root of rho square root of Em. Okay, because what we do now is we multiply from the left with rho to the power of minus 1, so with the inverse, such that we bring this one to the other side. So we have Cm and then rho minus 1, and then this one here, and then rho minus 1/2 em is equal to em. Okay, now let's write this as follows. So first we define this as operator d. Okay, so we can write this as Cm times d minus the identity times square root of em is equal to 0. Okay, so what you see here is d is simply composed of some invertible rho, and sigma is also normal, so this thing is normal. We can use the spectral decomposition for it. So we use now the spectrum composition for d. So now let d equal to sum over j dj cat dj be the spectral composition of d. Okay, and now remember what we actually want to do. Okay, what we want to do is we want to find a POVM such that this holds. Okay, because we want to find a POVM such this inequality saturates, and we've just seen that it does saturate if this equation holds, right? So we want to find a set of measurement operators for which this is true, and we have the freedom to choose this set of coefficients Cm. Okay, so we have the freedom to choose these coefficients and the freedom to choose these measurement operators. Okay, and what we do now is the following. We choose those as follows, and choose the measurement operators Em as the projector on these eigenstates of D. Okay, so and we know that this is also the square root of Em. Okay, because it's a projector. Okay, if you square it, it remains the same. And we choose this, and the coefficient Cm we choose as 1 over dm. You will see in the second why. Okay, because now let's plug this all in. So then we have, for the coefficient Cm, we chose 1 over dm. And then we have the spectral decomposition. Minus identity. And then we plug in Em as this projector, dm. Sorry, here must be coefficient, must be m. So it's dm. This times this must be 0. So, and there's one more line until we see that this is true. So let's now multiply this out such that we get 1 over dm, and then the sum vanishes because we have this projected dm here, and the sum vanishes, and we get dm dm dm, and then minus dm dm equals 0, and this is true, meaning that we just found a pure VM such that this inequality saturates. Okay, and this finishes. No, it doesn't finish the proof yet, because what we assumed is that at some point we assumed here that rho is invertible. Okay, that meaning that it is positive definite, but in general rho can be positive semi-definite. Okay. So in this case is actually how one does this case is one argues that this result also holds for rho having some eigenvalues equal to 0, because if it has eigenvalues equals to 0, it's not positive definite anymore, but positive semi-definite. And one argues this by continuity, meaning that take those eigenvalues which are equal to 0, okay, in a limit. So suppose that it has non-vanishing eigenvalues, but in a limit, and these eigenvalues vanish, okay? And then take this limit, and this limit must be continuous. And by continuity, you then can argue that this also must hold if rho is positive semi-definite. Okay. So meaning, let me state this again. We have now to show that this also holds if I have some eigenvalues equal to 0, right? Suppose now that these eigenvalues are infinitesimally small, okay, in some limit, and this limit must be continuous, meaning this result must also hold in this limit, and with this one can argue that it also holds if rho is not invertible. So the case of non-invertible rho, meaning if rho has eigenvalues equal to 0, follows from continuity. Okay, now we are finished. Okay, so we just proved that the fidelity now provides a lower bound to the classical fidelity if I perform measurements on rho and sigma. Okay, and we've just seen that this is kind of a very similar property to the property of the trace distance. And now we're going to state two more properties which are similar to those properties that we showed for the trace distance. The first one is the monotonicity of the fidelity under trace preserving quantum operations. So it's theorem 3.9. That's the monotonicity. And it's as follows. So let rho and sigma be quantum states or be density operators on the Hilbert space H. And then if E is a trace preserving quantum operation, then we have that the fidelity of E rho E sigma, so after this trace preserving quantum operation, is greater or equal to the fidelity of rho and sigma. So the proof, I leave the proof as an exercise. Don't know whether we do this in the exercises or not, but consider it as an exercise. Okay, what does it tell us? If we have a trace-preserving quantum operation, then it means that after this trace-preserving quantum operation, we have a higher fidelity. Okay, kind of a similar statement to the trace distance. For the trace distance, we've seen that after a trace-preserving quantum operation, the distance gets smaller. Okay, so now suppose we have a Hilbert space. After this trace operation, the distance gets smaller. Take a Hilbert space. Suppose here is rho and here's sigma. Okay, and now suppose that we have some operation E such that here is E of rho and here is E of sigma. So after this operation, they are closer together. And the fidelity, as we said, is kind of a similarity measure. And this tells us now after this trace-preserving quantum operation, they are more similar. Reason because they're closer in Hilbert space. Okay, this is what it tells us. Okay, then let me directly come to the next property, which is the strong concavity of the fidelity. So remember, for the trace distance, we proved that it is strongly convex. And now we simply state that the fidelity is strongly concave. So it's theorem 3.10. It's the strong concavity. Of the fidelity. So let Pj and Qj be probability distributions. And the set rho j and sigma j be density operators. On the same index set or over the same. Okay, then we have that the fidelity of the sum of j, bj, rho j, and sum of qj, sigma j is greater or equal to the sum over j square root pj, qj, and the fidelity of rho j and sigma j. So this 3.106. So this is called the strong concavity. Okay. Remember that for the trace distance we had strong convexity, meaning that instead of greater equal we had smaller equal. And well, again, we're not proving this this property. Simply state it. The reason that it's actually an important property, which is useful if you work with ensembles, because you see that on the left-hand side the argument is an ensemble of quantum states. And whenever you work with such classical ensembles, by classical I mean an ensemble connected with some classical probabilities, so suppose you work with an ensemble, then this property is important once you want to know something about your ensemble which is related to this fidelity. Okay, so this theorem is called the strong concavity, and from this we also find that the fidelity is concave in its first entry. Okay. So the proof is an exercise. And let me do the following remark. Namely, by theorem 3.10, we find that the fidelity is concave in its first entry. Namely that f of sum over j pj sigma j rho is greater or equal to sum over j pj f of rho j sigma. And by the symmetry, of the fidelity, it is also concave in its second entry. Okay, with this, I'm finished with stating all the properties that we need for the quantum fidelity. And as I already highlighted a couple of times, we see a clear relation between fidelity and trace distance, right? Kind of they behave opposite to each other. And this we can really see with all the theorems that we stated. So in particular this theorem now 3.9, 3.10, and 3.8, okay, which was the connection to the classical measure. And similar theorems, we formulated similar theorems for the trace distance in theorems 3.4 to 3.6. With a kind of opposite behavior. So let me briefly write this down. By comparing the properties of the fidelity, so it was theorem 3.8 to 3.10 with the properties of the trace distance which we stated in theorem 3.4 to 3.6. We see that the fidelity behaves opposite to the trace distance. Okay, and what this suggests now is that it suggests that there's a relation between the trace distance and the fidelity. And this is going to be our next section. Namely, the relation between those two measures. So remember that we defined these measures in order to compare quantum states, right? And you can choose now trace distance or fidelity, okay, whatever you like. They have kind of similar properties. And as we will see in a second, they are related to each other. So usually, okay, there is actually no kind of measure which one typically chooses. It kind of depends on which field you're working at, or what in particular you're working at. Because we've, for example, seen that the trace distance satisfies all the properties for being a metric. So it might be favorable to choose the trace distance to compare the quantum states. On the other hand, it might also be favorable to choose the fidelity for some reason. Okay, so yet we didn't kind of specify to prefer one of them. And indeed, you can actually use the measure you like in the end. In particular, as we will see next time, if you compare pure states, then the fidelity and the trace distance are related by an equality. Okay, so meaning that they serve equally well to compare the states. If you have pure states, if you have mixed states, they are related by an inequality. Okay, or actually by two inequalities, and those two inequalities are the so-called Fuchs-van de Graaff inequalities. Okay? And this we're going to state now as a theorem, and we prove the theorem the next time. But let me now state the theorem. So it's section 3.2.4, the relation between trace distance and fidelity. So it's theorem 3.11. They are called the Fuchs-van de Graaff inequalities. So the fidelity f of rho and sigma and the trace distance d of rho sigma of the quantum states rho and sigma satisfy that 1 minus the fidelity of rho and sigma is smaller or equal to the trace distance of rho and sigma is smaller or equal to the square root of 1 minus f square root of rho and sigma. So this is the squared fidelity. Okay, so this is the Fuchs-van de Graaff inequalities, which now connect fidelity with trace distance. You see that there are two inequalities. And as I told you, we're going to prove this next time. So we're going to stop here and start the next time with proving this. And then we're going to take a look at some special cases. So we take a look at how do they look like if one of these states is pure. And then we take a look at how what happens if both of these states are pure. Okay, so that's all for today, and we're going to prove it on Monday.